In this lesson, we'll learn about functions and relations. We'll start by looking at relations because relations are a superset of functions, or functions are a subset of relations. That is, every function is a relation. Not every relation is a function. So let's start by looking at what relations are. A relation simply describes how one set of values relates or maps to another set of values. Relations create pairs of values, and those pairs of values will be related to each other according to the relation definition. So some examples are the pairing between people in our class and their birthdays, for example, or people and their pets. So each person in our class has a birthday, and so we could create pairs of values where the first value is the person's name and the second value is the person's birthday, and that would be a relation. We could create, we could have a relation that relates people with their pets, and then it's possible that we might have pairs with a person, and if that person has multiple pets, then we would have multiple pairs that specify that person as the first value and each of their pets as the second value. So those are some non-mathematical examples of relations, but we also have mathematical examples of relations. So we could pair some set of numbers and the result of multiplying each number by 2. So for example, if we had a set of numbers 1, 2, and 3, and we define this relation as s times 2, then the pairs that would result from that would be 1 and 2, because 1 times 2 is 2, and then another pair would be 2 and 4, because 2 times 2 is 4, and the third pair would be 3 and 6, because 3 times 2 is 6. So we have a set of numbers, we apply the relation to that set of numbers, and we end up with a set of pairs as a result. Now, functions are also relations, but they have a special condition, which is that each element in the source set maps to only one element in the result set. So if we consider the values that are generated by our relation as pairs of x, y values, it doesn't have to be x and y, but we're used to hearing about x and y values because we tend to map functions and relations that are mathematical on a coordinate plane when they're two-dimensional. So if we have pairs x, y that are generated by a relation, that relation is a function if for each x there's only one y that can result from that relation. Then that relation is a function. Said another way, a function takes inputs and produces a single output for each input. And this is where the term functional programming comes from. In functional programming, we define functions or procedures, and for any particular input, we're guaranteed that that function will always produce the same output. We'll only ever get one output for any given input. Now, it is possible that two different inputs produce the same output. That could still be a function, but what has to be true is that for any input, we only get one possible output. So let's look at some different ways that we can understand this requirement of functions. One way of determining if a relation is a function or not is using a mapping diagram. In this example, we have a relation that's defined as the square root of x. So the square root of x is not a function because, and you may or may not be aware of this, but for any number, we have both a positive and a negative root. So if, for example, we take the value 1, the square root of 1 can be -1 or 1, and that's because -1 times -1 is 1, and 1 times 1 is also 1. Likewise for 4, -2 times -2 gives us 4, just like 2 times 2 gives us 4. So for any number, each number has both a positive and a negative root. And that means for any x, we have two possible outputs, and this breaks the rule of a function. So the square root of x is not a function because each element in the domain maps to two values, the positive and the negative root. Here are some examples of relations that are functions. So on the left we have f of x, this is just notation for a function definition, is x times 2. So in this case, no matter what x we plug in here, we're always going to get a single output. So 1 times 2 is 2. 1 times 2 is nothing else. 1 times 2 is always 2. 2 times 2 is always 4. It's never anything else. So for any input that we provide to this relation, we get a single output every time, and that makes this relation a function. On the right-hand side, we have f of x equals x squared. And similarly, any number we plug in here, if we have 0, 0 squared is always 0. -1 squared is always 1. 1 squared is always 1. So here's a case where we have two inputs that map to a single output, but this is still a function because no matter which value we pick as an input, we always get a single output based on that input. So both of these are examples of functions. Now there are different ways that we can represent functions. One way that you may remember from school is a graph. So we can graph a function on a coordinate plane where the x values are on the horizontal axis and the y values are on the vertical axis. And so this is a representation of x squared. So when x is 0, y is also 0. When x is 1, 1 squared is 1, and y is 1. When x is -1, -1 squared is also 1, so y is 1. So this is a graph of a parabola, which is the graph that we get for f of x equals x squared. We can also represent a function as just a number of pairs. But if our domain is unlimited, if our domain is infinite, like if our domain, for example, is all integers, then we would be writing pairs forever. So writing pairs isn't necessarily the most efficient way or a reasonable or practical way to express a function. But we can express a function in terms of the pairs that are produced by the applying the function to a domain. Often we express a function as an equation, and this is a nice succinct way, generalized way to express what our function represents. We can also express a function in code as programmers. So we can define, for example, a function called power2 that takes in an input, a number, and returns that number squared. And this is also an example of a function. Functions have a domain and range. You may remember the word domain from studying sets. In sets, the domain is the set of all possible values from which our set can be defined. When we're talking about functions, the domain is the set of all possible inputs to our function. And all possible outputs are for those inputs in the domain is called the range. So we say that we can map a function over the elements of a domain to produce the range of values. Let's look at the notation in this example. We have some set of values labeled as capital X. So we have the values 1, 2, 3, and 4. And then we have a function defined as f of x equals x plus 1. And we're told that we're going to map f of x over the set x. What that means is we're going to apply this function x plus 1 to each of the values in this set of values x. So we'll apply it to 1 and 2 and 3 and 4. So in this example, the domain is just our set X. It is the values over which we map the function, or the values that we plug into our function. And the range is the result of mapping that function over each value, or the result of applying that function to each value. So in this case, we get 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, and 4 plus 1 is 5. So our range is 2, 3, 4, 5. Now, just like with any relation, when we apply a function to a set of values, we also can say that we generate pairs of values. So pairs of values that relate to each other according to this function. So the pairs that are generated contain the x and y values, where the x value is the value from the domain, and the y value, the second value in the pair, is the result of applying the function to that x value. So here, if the x value, we start with the 1, we apply the function, we add 1 to it, then the y value we get back is the 2. When we provide the 2 from the domain, the y value we get back is the 3. We input the 3 into our function, the value we get back is the 4. When we input 4, we get back the value 5. So these are the pairs that are generated by this function, and we could graph these pairs of values on a coordinate plane. So looking at the pairs of values that are generated by the function, we can see that the domain consists of all of the x values, 1, 2, 3, and 4. So these are the x values from our pairs. And the range are the y values from our pairs, 2, 3, 4, and 5. Now that we understand the difference between functions and relations, or what makes a function a special kind of relation, now let's talk about properties of relations. So we're going to look at 3 major properties of relations. There are some others, but these 3 are commonly referred to. So the first one is called reflexivity, or the property of being reflexive. And the property of being reflexive says that x relates to y, is the relation R is reflexive if and only if x equals y. So if this relation is reflexive, x relates to y if and only if x equals y. This IFF is a shorthand for if and only if. So reflexivity is the property that holds when for all elements in the domain, the relation pairs each element with itself. The most common example of a reflexive relation is equality, or equals. The relation equal to on the domain of all numbers is reflexive because every number is equal to itself. Let's have a look at another relation that is reflexive. So here we have a relation R, which is defined as x is greater than or equal to y. So when we consider this relation, first of all, if we're not given a domain and we have a numeric or mathematical relation, then we can assume that the domain is all numbers. So any number. So for any number, in order for this relation to be reflexive, it must be true that for any number, any input, any x value, it must be paired with itself by this relation. So if we consider any number for x, so let's say that x equals 1. If x equals 1, then we do have the pair 1, 1, where y equals 1, because x is greater than or equal to y. So if x equals 1 and y equals 1, then this relation holds true because 1 is greater than or equal to 1. Now we also get some other pairs that are formed by this relation. So for example, 1 is also greater than or equal to 0. So in this case, we could have a y equals 0, and 1, 0 would also be a pair that is defined by this relation x is greater than or equal to y. So we can think of any number for x, and we can always find multiple y's for which this relation holds true. So for example, if x equals 3, well, the relation holds true for y equals 3. It also holds true for y equals 2 and for y equals 1. And if we have, and also for y equals 0, so we have the pairs 3, 3 and 3, 2 and 3, 1 and 3, 0. And if we're including negative numbers, then we also have all of the negative numbers to infinity, right? So it doesn't matter that we have these additional pairs that pair x with some other value, as long as our relation always pairs x with itself. Always pairs x with itself. And for any number that's true, if x equals 2, this relation pairs 2 with 2 because 2 is greater than or equal to 2. So as long as the relation pairs a number with itself, that relation is said to be reflexive. And what gives this away is this equal sign here. So y greater than or equal to x greater than or equal to y is reflexive. X less than or equal to y is reflexive. X equals y is reflexive. All of those are examples of reflexive relations. The next property we'll talk about is transitivity. So a relation is said to be transitive when, if x relates to y and y relates to z, it implies that x relates to z. So transitivity is the property that holds when for all elements in the domain, for any 3 elements, if the relation pairs x and y, and it pairs y and z, it also pairs x and z. So transitivity requires examining 3 elements that are involved in our relation, or that our relation can be applied to. And the best examples of relations that are transitive are comparative relations. So comparative relations are always transitive. So comparative relations are relations with the word than in them: less than, greater than, bigger than, smaller than, taller than, shorter than, older than, younger than. All of these relations, it holds true that if x relates to y and y relates to z, then x relates to z in the same way. Let's think about an example. So if we consider less than, if x is less than y and y is less than z, that implies that x is less than z. If we use actual numbers, if 1 is less than 2 and 2 is less than 3, that implies that 1 is less than 3. So that is transitivity. Comparison relations are transitive. Note also that transitive relations cannot be functions, because for any particular input, there will be more than one output. So for example, if 1 is less than 2 and 2 is less than 3, then 1 is also less than 3. That means that 1 is less than 2 and 1 is less than 3. And 1 is less than 4 and 1 is less than 5 and 1 is less than 6. So in transitive relations, these relations are never functions because the input always maps to multiple outputs. Another way that we can look at these properties is using a relation matrix, and it can help us to see visually when a relation has certain properties. So let's have a look at that. To draw a relational matrix, we fill in the dots where our relation holds true for values of x and y. In other words, where we have pairs of x and y. So if we look at the values here, we have x on the horizontal and y on the vertical. And so for the value 0, if we apply x equals y, then the y value that holds true for is just 0. So we get 0, 0. We also get 1, 1, and we get 2, 2, and we get 3, 3. And those are the only pairs, given those input values, those are the only pairs for which this relation holds true. So we can fill in the dots that correspond to these pairs. So here's 0, 0, 1, 1, 2, 2, and 3, 3. Now notice that we have this diagonal that is formed, and that diagonal across the center of our relational matrix is the visual indicator that this is reflexive. As long as that diagonal row of dots in the center is filled in, the relation is reflexive. So let's look at another example where we have x is greater than or equal to y. So given the values of x that we have here, what pairs satisfy this relation? Well, for 0, 0 is greater than or equal to 0. That's the only value of y for which that is true. What about for 1? Well, 1 is greater than or equal to 0, and 1 is greater than or equal to 1. So for those two pairs, with that value of x, this relation holds true. What about for 2? Well, 2 is greater than or equal to 0, and 2 is greater than or equal to 1, and 2 is greater than or equal to 2. All right, so what about the value 3? The value of x is 3. 3 is greater than or equal to 0, and 3 is greater than or equal to 1. 3 is greater than or equal to 2, and 3 is greater than or equal to 3. Now, if we fill in the dots in our relational matrix that go along with these pairs, we have 0, 0, then we have 1, 0, and we have 1, 1. Then we have 2, 0, and we have 2, 1, and 2, 2. We have 3, 0, 3, 1, 3, 2, 3, 3. Now, notice that even though we have dots filled in on the upper half of our matrix that are not filled in on the bottom half of our matrix, we still have this center diagonal filled in, and that means that it's reflexive. Now, when a relation is also transitive, we'll see this behavior that the one side of this diagonal is also completely filled in. So we'll see this indicates that this relation is also transitive. But it's still reflexive because that central diagonal is filled in. The last property that we'll look at is symmetry. Symmetry says that if x relates to y, this implies that y relates to x. In other words, symmetry is the property that holds when for all elements in the domain, if the relation pairs x and y, it also pairs y and x. A non-mathematical example of this is cousins, because if Ted is Susan's cousin, then Susan's also Ted's cousin. We could also say the same about siblings. So if one person is another person's sibling, then the other person is the first person's sibling as well. So those are examples of non-mathematical relations that are symmetric. We also have mathematic examples. One is addition and another is multiplication. because if, for example, we have the relation x plus y equals 5, that would be symmetric because for every xy, there is also a yx. So for example, if x is 1, then y is 4. And if x is 4, then y is 1. So we always have the symmetric pair when we have a relation like this addition relation. And the same would be true for multiplication. Let's have a look at a relational matrix that shows symmetry. So in this example, if we have x plus y equals 3, then what are the pairs given these values, possible values of x and y? We would have 0 and 3, and we'd have 1 and 2, and we'd have 2 and 1, and 3 and 0. So we can see just by looking at the pairs that we have symmetry. So we have these two pairs, and we have these two pairs, and these are symmetric. And if we draw into our relational matrix, we'll see it as well. So we have 0 and 3, we have 1 and 2, we have 2 and 1, and we have 3 and 0. So notice that again we have a diagonal, but it is going in the other direction. So this diagonal does not demonstrate reflexivity. This diagonal demonstrates symmetry. Let's look at another example. Here's another example where we have a relation defined as x plus y is divisible by 2. So this symbol here, this pipe symbol in this context means divisible by. You might remember this from the lesson on sets. So x plus y is divisible by 2. Another way of saying that is the sum of x and y is even. So let's look at the pairs that for which this relation is true, given the values 0 through 3 for x and y. So we have 0 and 0. We have 0 and 2. And then we have 1 and 1. And 1 and 3. And then we have 2 and 0, 2 and 2, and we have 3 and 1, and 3 and 3. So for each of those pairs, this relation holds true. The sum of these pairs of numbers, each pair is an even number. And we can also see right away that there's symmetry here. So let's find the symmetric pairs. So we have these two pairs, and we also have these two pairs. Now, notice that the other pairs that are here, that I didn't draw lines between, well, they're pairs with the same value. So if we had a 0, 0, then it doesn't make sense to have another 0, 0. Oh, here's another one that I left out. So if we fill in, let's fill in the relational matrix and see what this looks like. So we have 0, 0, and we have 0, 2. Then we have 1, 1, and 1, 3. We have 2, 0, and 2, 2, and we have 3, 1, and 3, 3. So one thing to notice is that this relation is reflexive. And if we folded this relational matrix on that diagonal axis here, if we folded it here, we would see that these values would match up. they would sit on each other. So if we folded it in half, we would see the symmetry of this relational matrix. So it is also symmetric. So let's just practice with a couple of examples. What would the properties of these relations be? And the first relation, and noticing also the syntax and notation. I've exposed you to several different kinds of syntax here. All of them are valid syntax to express these concepts. So here we have a syntax that says that x relates to y such that x is greater than or equal to y. So this is the relation defined as x is greater than or equal to y. And the properties of this relation are reflexive because of the equals and transitive because of the greater than. So it's reflexive and transitive. What about the second relation? This notation says the pair xy is an element of the relation R if and only if x is less than y. So that's the way that you would read this notation. Another way to say it is the relation is x is less than y. So what are the properties of that relation? It's just transitive because of the less than. It's not reflexive because if x is less than y, that means that we never pair a value with itself. 1 is not less than 1. 2 is not less than 2. And it's also not symmetric because 1 is less than 2 and 2 will never be less than 1. So it is only a transitive relation. The best way to get comfortable with the concepts in this lesson is to practice, to look at different relations, different notations, and to get familiar with those, to have a look at different relations and their properties and make sure you understand why those relations have those properties, and also practice distinguishing what makes a function. So recognizing that functions have the property that for every input there's only one output. And then finally practicing recognition of the domain and range for a function.